Welcome to the next part of this FPGA development board tutorial series. In this video, we will explore how memory blocks can be used inside an FPGA to generate predefined data patterns. We'll begin by introducing a single-port ROM, where the memory contents are initialized using a hex file. Then, we'll see how a counter is used to sequence through ROM addresses, allowing different data values to appear on the FPGA output pins. Finally, we'll demonstrate the design on actual hardware, where the ROM data is observed as changing LED patterns. This example builds on the earlier concepts of clocking, synthesis, and flash programming, and introduces an important idea used in many real-world FPGA designs: lookup-table-based logic. Let us now begin with the ROM-based example. The Verilog code shown here is the top module used in Part 5 of this tutorial series. The timescale directive specifies a simulation time unit of 1 nanosecond and a time precision of 1 picosecond. This is mainly relevant during simulation and does not affect the actual FPGA hardware behavior. The module is named top and has two ports, CLKIN and DAT. The input CLKIN is the system clock provided to the FPGA, typically from the onboard oscillator. The output DAT is a 4-bit wide signal, which will be driven using data read from an internal ROM. Internally, a 27-bit counter, named count, is declared. This counter increments on every rising edge of the clock input. The counter acts as a clock divider, where the higher-order bits change slowly compared to the input clock. Two internal signals are declared next: ROM_data, which holds the data read from the ROM, and ROM_ADDR, which represents the address supplied to the ROM. The ROM address is generated using the three most significant bits of the counter, specifically bits 26 down to 24. As the counter increments, these address bits change slowly, causing the ROM to be accessed sequentially, one address at a time. The output DAT is directly assigned to the ROM output ROM_data, so whatever data is stored at the current ROM address appears on the output pins. The next part of the code instantiates a single-port ROM module. The ROM is configured with a data width of 4 bits and an address width of 3 bits, which means it contains 8 memory locations, each storing 4 bits of data. The contents of the ROM are initialized using the file rom.hex, which contains the predefined data values. The ROM address input, clock input, and data output are connected to the corresponding signals in the top module. As a result, the FPGA continuously reads data from the ROM at a slow rate determined by the counter, and the ROM contents are observed on the DAT output pins. This example demonstrates how a ROM can be instantiated and accessed in an FPGA, and how a counter can be used to sequence through memory addresses for hardware-based pattern generation or lookup operations. To generate predefined output patterns, we use a small memory block inside the FPGA. The Verilog code shown here implements a simplified single-port read-only memory, or ROM, with a registered output. The module is named single_port_ROM and is written in a parameterized form, allowing flexibility in memory size and data width. The parameter data_width defines the number of bits stored in each ROM location. The parameter ADDR_width specifies the number of address bits, which determines the total number of memory locations. The parameter RAM_init_file gives the name of the file used to initialize the ROM contents. Based on the address width, the total memory depth is calculated as to raise to the power of ADDR_width. Internally, the ROM is implemented as an array of registers, where each location stores data_with bits of data. During initialization, the readmemh system task is used to load the contents of the ROM from the specified hex file. This occurs once during configuration or simulation startup. The ROM is accessed synchronously. On every rising edge of the clock, the data stored at the address provided on the ADDR input is read from the ROM. This data is then assigned to the output register data. Because the output is registered, the ROM data appears at the output 1 clock cycle after the address is applied. This registered output ensures stable and predictable timing behavior when the design is synthesized on the FPGA. This module demonstrates a single-cycle, clocked ROM, making it suitable for lookup tables, pattern generation, and simple memory-based control applications in FPGA designs. Let us now demonstrate the ROM-based output on actual hardware. The 4 output bits DAT3 down to DAT0 are connected to 4 LED indicators through the output connector. The ROM is initialized with 8 hexadecimal values in this order: 1, 3, 7, F, E, C, 8, and 0. As the FPGA runs, the counter generates the ROM address, and the ROM output appears on the 4 LED indicators. You can observe the LED pattern changing step by step as the ROM addresses advance. First, the LED indicators display 1, which is binary 0001. Next, it changes to 3, binary 0011. Then 7, binary 0111. After that, it becomes F, which is 1111, so all 4 LED indicators turn on. Next is E, binary 1110, followed by C, binary 1100. Then 8, binary 1000. Finally, the output becomes 0, binary 0000, so all LED indicators turn off. After reaching the last value, the sequence repeats again from the beginning. This confirms that the ROM is correctly initialized from the hex file and the FPGA is reading the memory contents sequentially and displaying the data on the hardware LED indicators. With this, we come to the end of this part of the FPGA development board tutorial series. In this video, we demonstrated how to use a single-port ROM inside the FPGA to generate predefined data patterns, and how these patterns can be observed on the hardware using LED indicators. This example showed the complete flow of ROM initialization, address sequencing, and registered data output using Verilog. For a detailed explanation of pin assignment using the Interface Designer and platform flash programming with the CH341 programmer, please refer to the previous videos in this series, where these steps are covered in detail. In the next part, we will move on to more advanced memory-based and logic-based FPGA experiments, building further on the concepts introduced so far. Thank you for watching, and we'll continue with the next part in the upcoming video.